I'm Thomas Piatrick from Queen Mary University of London, and I'm part of, we are part of Multimedia and Vision Research Group. When I came to this meeting yesterday, and mostly after talking to people and today after seeing all these presentations, I realized I'm really in the company of big experts and high caliber people in microscopic field, and I really admire all this work, but I have to admit I have no idea, guys, what you are talking about and how you manage to build these things. But I am truly fascinated, and I admire this kind of work. On the good, as a positive news is that we really don't have to understand exactly how you are doing it, because what we are really good at in our group is image processing. And for us, as soon as we work on a pixel level, that what matters to us, and we can really do some magic. And I will try to show you in this presentation a couple of applications we have been working on with different end users. And although some applications will look like very unrelated, they are all related on some level. And I will try to explain why I'm showing all these. But at least you will now have a chance to take a rest from microscopes and maybe relax and enjoy a different type of research. So we are part of the university which happens to be very high ranked in research in UK, and is one of the leading universities in computer science and electronic engineering. And our group, we call it MMV, Multimedia and Vision Group, is around 18 years old, and currently we have around 1 million of active research grants, and since 2010 it has been 15 million, usually coming from European projects or different sources of funding, or cooperations with big companies, which I will talk about a bit later. And since 2010, there have been around 25 PhD students graduated from our group. And of course, one of the outcomes, as we are mostly solely focused on research, is producing high quality papers and journals, as any research universities do. Now, when it comes to projects, since we started, we have been participating in many European projects. All these are European projects. They last between 3 to 4 years, connecting different partners in Europe or beyond Europe. And I'm not going to talk about them, don't worry, but just to give you a brief overlook, that we have quite extensive experience in European projects. And since, I think this is like the last 5 years, we have become very active in security domain. These are just some key projects that we have been doing, again funded by European Commission. And the first 3 are very recent ones, which are running at the moment. And we work with different police units in Europe. And we use image processing mostly and video processing to tackle different challenges and certain applications in there. I will discuss some of them later. And we do enjoy very close collaborations with some big players. We are very appreciating this. I put BBC on the first place because some of the people who are coming from our group, some of the first PhD students, became running a BBC research unit. So we have very close collaboration with them, and almost half of the students from our group are spending half time in BBC and back and forth. And we do work on video processing and video coding for BBC. And we have very close collaboration with Scotland Yard, and I will show some applications for that. And a couple of other companies. I'm not going to go through all of them, but we do also 3D reconstruction with Disney and Microsoft and so on. And when it comes to security, because of course this project is also very related to security, we have enjoyed cooperation with many companies, and mostly, I mean, some companies are on this side. These are the technical companies which we work with, either part of European projects or on more mutual basis. But there are many end users here. Scotland Yard is one of them, but we work with many police forces in Europe. Also, it's Israel police. I noticed one of the partners is from Israel, so we do work with them in 2 different projects. And this is what we mostly do. Everything is basically turning around image and video processing, but also 3D reconstruction, video coding. We are very strong in video coding, and so on. I'm not going to go through all that, of course, because this particular project is very focused. But I want to show you some applications which I picked up to demonstrate the challenges which we have to face in those, and what is the relation between what will be the challenge and how we can tackle it in this project in SHUTTLE. So when it comes to image processing or video processing, because when we process videos with basically static images, or as we call it, frames, and the only difference is that in videos we have to also consider temporal information between frames. So what we do on the first, as a first processing step, we try to extract objects which are moving in a video and to create some kind of separation between foreground and background. Now this might sound to some people as quite simple task. It's not. It's a very difficult one, mostly because you have very different cases where camera might be moving, or there might be shadows or illumination, or background might be moving, some trees. And we have to do it real time. And this is the most challenging part. Because if we don't do it real time, any kind of further processing that we want to do on those objects which are extracted as a foreground would not be real time anymore, right? So this is the biggest challenge we have to face, and we do it real time, and we can even process very high resolution videos and do it real time. I can show you some. Give me a second. Some okay. This is low quality. Give me, okay. Okay. So yeah, it's very low quality. I'm sorry for that, but basically this is what we are talking about. So we are trying to first extract what is the object that could be part of the foreground, and then do further processing on that. This image is for the next slide. So what can we do with that? So once we have a foreground extracted from the video, we can do all sorts of applications on that. We can do all sorts of detection. This is one of the applications. We do detect drones and track drones. As you know, this is very high topic, booming topic at the moment. Even after recent cases, what happened in the UK, and Gatwick has been closed, and Heathrow. So this is, we do part of the European projects. Israel police is also part of it, and Belgian police and Romania. And it is on the coast, so basically border police want us to detect any kind of objects flying, mostly drones, because criminals use drones to snaggle drugs and different kind of tactics they use. So we do a lot of processing here. Everything needs to happen real time again. We process full HD video, so you can imagine the power of the computation we have to do if we want to do it real time. And we do all sorts of processing steps in one go. Of course, we use deep learning networks mostly to detect drones. The tricky part is that when you have a very small, tiny drones flying, it's very difficult to distinguish between seagulls or birds. And we don't want to send police false alarm every second or every minute. Yeah? So this is what we have to tackle. I'm going to show you. This is the hardware part of the system that has been built in this project. So it's really something tangible. It works also with 3D LiDAR. We are not responsible for that part, but we are responsible for the unit which is having different cameras on it, including night vision cameras, infrared camera, gated camera, and so on. And on the next video, you can see some detections from different cameras or different scenarios where you have a night and so on. I want to show you some examples how, where is my mouse? Here. How we test the different very difficult challenges. Like for example, when drone disappears behind the sun, let's say. So the algorithm has to, I think I skipped that part, but the algorithm has to really cope with that kind of challenges where the temporal information where is very tricky, important to consider. Otherwise, if we process drones only as a static images, is not going to work. Yeah, and the different ones. This one was to show how tiny, small objects we can detect. It can be even smaller, and we can still distinguish between drone and bird. And then this is maybe from the infrared camera. Again, drone can completely vanish behind some clouds, and we are still able to track it, even though human eye might not notice that. So this is some kind of work we are doing. Okay. Now, when it comes to cooperation with Scotland Yard and Metropolitan Police, it's the same, but is well known for a name of Scotland Yard. We do some work with them. Of course, you see here face detection and recognition. This is very standard work that many research organizations have been doing. But in here, what we faced was quite a big surprise. When we came to start cooperating with them, we discovered they are not using any face detector or any face recognizer. And we asked why. I mean, there is already on market so many solutions, and they say, well, just bring us something that is going to work, because nothing works so far. And many of you might be also puzzled why, because seriously, I mean, Facebook is using one of the state-of-the-art solution, and it works very well, but not on that kind of data. And these are the real cases that they have to tackle with, and you don't really see. Or at least you can see there is a face, but machine learning or automatic detector, it would fail on those. So we, as a group, cooperate with them. This is maybe for last 6-7 years, and try to build a solution for them. We already managed to build a solution which they use, and it's working on that kind of data. So when we talk about traces, and if something is not completely sharp, we have some expertise how to tackle that. To some extent, of course. If it's very blurry, then it's tricky. Then, of course, then we have to also consider that if we do face recognition, some faces are going to look different. If it's the same person and from different age, we are able to still learn and try to get a signature for a specific person to figure out that this is the same person as this one, based on some facial features that we can extract. And we can take it further, of course, and we can combine it with the clothes and not only the appearance of the person, but also the way person walk in the video, and so on. And we can bring more semantics into it. When we talk about that, I just want to mention that we have good expertise in ontology. So sometimes we have to use ontology to create a more higher semantic knowledge of what is happening in the scene. And this is really useful for police to be able to learn from the past cases and to bring out something from the past and see the relationship between some something would happen is happening now and being investigated now, and something would happen in the past from their data. Now, okay, this is all fine. Again, we were very excited to be proud bringing solution to Scotland Yard, but then they bring another problem, and they say, can you help us to identify this person? And this is not a specific case that happens very rarely. This is actually something that they have to deal with almost on weekly basis. These are the pictures that they need to process, and this is the person they're looking for. So face detector, or face recognizer, is completely irrelevant here, because even human cannot see who is that, yeah? And we had to find a solution for them, and we did it. And the way we do it, and I will try to explain it on this very simple example. Something happened here. These are real cases, so I'm using from there the data that they gave us. Something happened to him. There was a fight and robbery. And they're interested in this person when you cannot see, because the camera is CCTVs are so low quality, and even he's using how to say, hoodie. So that person is a suspect. What we can do, however, we can detect or let the investigator to tell us what is the distinctive region that is representing that person. In this case, is an orange zip. So we are focusing on orange zip. And we take that orange zip and we run it through, we use, of course, very complex algorithms to do that. And we process, we basically process all videos that they give us from all CCTVs in the region, let's say if it happens in London, in the District of London, terabytes and terabytes of data, hours of data. And we try to find that particular region. It can be logo. It can be logo on the t-shirt, on the hat, something that is distinctive for that person. And I can show you some video, but it's not, on this video, you're not going to see much, because this is just a so basically, for example, here we are looking for that kind of element on the t-shirt or hoodie, and we are able to go through loads of data and find that person. Why? Because that person, we can do also different things. Of course, we can focus on pattern, like someone has a red scarf, red. There was a person. Red scarf over the face. So this is different example. Yeah? So that person is of interest. Now, because you don't see person's face, but in some point they're going to put it down. And what police have to do, they have to track down that person manually. They put the officer in front of the computer, and that officer is going manually through hundreds of footage. It takes 2 to 3 weeks to find any clue. And that's how they operate now. And we managed to, through this video processing, we managed to put it from 2 to 3 weeks to 2 to 3 days for them. Because we filter out all the noise, all the footage that they don't have to even consider, and we try to pick where we believe, based on our processing, is this person. So very useful for them, and we are very happy to take part in that kind of stuff. Now, we were talking about a large scale of images. We do have expertise also on that. We work with 4K full UHD formats. This is work also in collaboration with BBC, and I want to show you what can be done with deep learning. It's magical to me. I'm not the one who is doing work behind this, but I find it fascinating. So we take a very high quality, high resolution video, and we split it into small blocks. And we split it between two sets. So one is high quality, one is low quality. And we feed it into the network that we built, the deep learning network. It's a combination of multi-layer and so on. And we let the network to learn how the low quality block supposed to look like in high quality. And after a lot of training, we get some kind of very interesting results. So let me show you what happens. You have a low quality image, for example, from CCTVs. Where is my mouse? Here. And let me explain you first. This, on this side, is the actual original quality of the video. So this is the concert of BBC. There is no better quality of that. It's the original one. On this side is what our algorithm can predict how the video could look like when trained before on the training data that we use it. So you can see that even the text is actually readable, while this is the original of the video. To me, this is really cool. What machine processing can do. And how this can, I mean, some companies find it very useful, especially not only media companies like BBC or any other content producers, but also police. Because why? Because sometimes they have to work with data coming from mobile phones or from CCTV, which is actually using low quality because it's coming from some producers from Asia and quality is very low. So they can see more. They can see details. Otherwise, they would be missing. Yeah, and to them, I mean, some of you are from police, so it's very important to get details. So this is another stuff that we do. Okay, we are getting closer and closer to SHUTTLE. So, and here we come to another collaboration that we do with Karolinska Institute, a hospital in Stockholm, who are one of the leading, if not the only one, I'm not sure, but they claim to be one of the few in Europe who do research on cancer from data coming from actual patients. And what they do, they have a diagnosis from patients, they have a pre-operational treatment, and then there is operation from where they extract the tumor, and then they assess the histology image, and based on that they can not only choose what is the best treatment for that person, but also to learn about how that particular type of cancer behave and how they can make it even easier next time to treat it in next cases. And this is our part. In Queen Mary we do this part. So we take histology images and we locate the region of interest, which for them is basically quantitative assessment of the tumor part, how big it is. We go to tissue and we detect and segment the structure of the tissue, and then we go to the cellular level and we detect the nuclear and the segmentation of that, and based on those things they can assess number of factors. I will just show later. So this is the different magnifications of the slide that they get from the tumor. So this is how it look on cell level, different tissue, in different cases, inflammation, blood, and so on. This is the tumor. So we have to basically train build a network and train it to be able to handle different classes, hierarchical classes, that they have to consider. And it's difficult because you look very similar to each other. Maybe not to the doctor, but to the machine learning, it does. So this is a big challenge, but we are doing quite well so far. I mean, from beginning it was challenging. Now we learn a lot. So the way we do it, we take on cellular level, we take cells, we position them, we segment them, and classify based on different kind of categories. On the tissue level, we do the same. We use different features to extract different things, and again classify the tissues. And based on that, we are able to tell which area was a tumor, but not only that, also which area is a how do they call it, metastasis? The growing of or the spread of the tumor. And based on that, they know what to do with that. We are not experts in medical side, but we help them with that. Okay, this is different look on the whole framework, but same framework, or at least a very similar one as this, we now, since last year, use also for microtrace image analysis, which we work together with Metropolitan Police. So we have some data from them, and we use similar framework. It's optimized and adjusted, so we have some different approaches here, how to tackle segmentation of different elements in traces. So here, for example, you got hair, and we use deep learning for that as well. And I'm not going to go deeper into the technical solution because that's going to be explained in the BIT application that we would like to submit with some of you, if you are interested to work with us. But basically what we do so far, and this is, as I said, this started last year, and we've been working with, so far, only with fibers and human hair. And we were able to classify different types of fibers, and not only color and texture-wise, but also the structure of human hair. And also we were able to, I mean, for that we didn't have enough data, but still some data of animal hair and human hair, but it was more on human hair level. And this is going on at the moment. Based on the technique which we developed and trained and tested also with Karolinska Institute, we are able to, of course, expand the training set for any kind of classes. So we are already discussing with Metropolitan Police about blood, about glass, that's it. But I can imagine some other elements which this would have to come from the users, the specification. And to us, doesn't really matter that much as long as we have data. And this is the biggest problem for us. When I heard you guys talking about 14,000 images, I was probably the only one in the whole room who was excited. Because we have opposite problem. Like with drones, you saw that. There is no data set on drones flying on the coast. We had to create one. We had to go to different locations to capture a lot of videos and then to annotate them manually so we can train the network. So for us, this is the challenging part. If we have a data, we can do something with it. The more data, the better. Of course, there are challenges. If the scalability is too high and you want us to get results very fast, we can work it out, mostly because the training phase can be done offline. So you take loads of data, you load it there, you let it train. It can train even weeks and months. The months doesn't matter to us. But once it's trained, the actual query is very fast. Okay, so for us, this is not a problem. But the data is a problem. So if we can get the data, we can do some magic with it. So that's all from my side. I hope it's not too late, a little bit. I hope we will manage to get a lunch. If you have any questions, please ask. I'm happy to, if I know how to answer, I'm happy to answer. Otherwise, we can also discuss during lunch. Thank you so much.
Could you elaborate a little bit more on this is very fast? Once the system is trained, the thing is very fast. You showed on the drones example, you could do a online tracking of the drone.
The drone system
is fast.
the drone system is real time. Why is it real time? This was the requirement from users. Why? Because the camera is on the tilted platform. And when drone is detected somewhere, camera needs to zoom in, but drone is flying. So the camera needs to track the drone, zoom out and zoom in based on the position of the drone in the video. We had no other option only to do it real time. But the video was HD. So yeah, it is not possible to do it HD in real time, but we were able to downscale to that extent that it was still possible to do the detection and tracking. So, yeah.
One mean comment. I think you have to redo some reference stuff on the previous slide. I'm not really convinced that it's cotton you have there.
Sorry? What?
I'm pretty sure this is not cotton.
You mean
the one on the top right?
This one? No. Some of them are just examples taken. I think those I took from those one.
Yeah, I don't think that's cotton.
Oh, I must have mismatched the classes.
Detail. Very nice.
But as you can see, I'm not really expert at distinguishing those. But I was trying to give an examples from the data, and maybe I'm.
Of course, just being mean.
Okay.
Sorry.
No, but
very nice
presentation. But yeah, very good point. Because once we have the right labels, this is what we need. Yeah.
More questions.
So maybe this is the same class, right? It seems like, or not? It's not.
I do seem to trust the acrylic.
I don't know.
That's from what I see, but not sure.
Okay.
The classification.
Yes.
You're doing the white on white. You classify white on white. Say. Sorry.
White on white. Can you elaborate a little bit?
Well, basically, you talk about tracking, and you did it behind the sun. But what happens if it was raining?
Yeah, so basically that's why we use, if you remember, there was a platform and had different type of cameras on it. Right. So some cameras there is one infrared camera, which obviously work also during the raining. There is a gated camera, which works very well when it's fog.
Right, so,
yeah.
So they have to be very, very complicated cameras to be used. Because it looked like you're using radar as well.
Yeah, we use 3D lidar, not standard lidar.
So basically, the camera's following the radar, tracking the drone.
Basically, it's 3D lidar who's supposed to detect objects if they are very far, because camera can spot a dot, but to certain distance. Yeah.
So you're using radar to track it.
We use lidar, 3D lidar, but once the camera zoom in, the video analytics takes place to recognize whether this is drone or bird. So
does it predict where it's going?
Yes. There is a fusion algorithm behind that takes all these inputs, and it does also prediction of the movement. Otherwise, the tilt would not be able to manage to track the object. So prediction is there. Yeah. But when you were asking white on white, the reason why it works is because we use also temporal information between frames. So normally, when it's white on white, the detection would be 0. There is nothing. But as there was drone before, we assume there must be drone somewhere there, even if it suddenly disappeared, because we use the temporal information between frames.
Is it when you have put a label on what you want to identify? Is it more simple to identify it again on a video or on a photo? Or
no. I mean, to us, video is photo. Okay.
Okay.
You have like 30 frames per second, so we basically break it into static images.
Okay.
And we only work with images, so it's always image. Okay.
Because a topic like a fiber can be on different images. So maybe the typical morphology that you want to to see is not visible all along the fiber, but at a specific place.
Yes.
So, but you have multiple image through the video.
If you remember when I was showing these videos, how we do upscaling, this is what we do. We break it into small blocks. So imagine big image, and we break it into small regions. So if we do it here, we would be able to concentrate on certain areas of that fiber. But it would be much better for us if we also get different magnification, like in the cases of the medical research we do. It will be better because then we can understand also how it looks on the, I don't know, I cannot call it tissue level, but I don't know how to use the right terms, but how it looks zoomed in and magnified and less magnified. So the network can learn on those different levels.
And other people spoke about the problem of the Z focus. That's a lot of data, but you can manage maybe to collect only in XY and use your algorithm to correct focus and non-focus area and just collect in
we can do that.
2D.
I was already thinking about that when you were discussing this. We can do that to some extent, and it does improve. Sometimes it doesn't improve because we artificially improve, so not always the positive result. But yes.
But you could try to train the sets on defocused images.
Exactly.
Yeah. If you would have a set of 100,000, there's the number again, 100,000 traces, and we have a data unit, say 1 kilobyte per trace. That's the information we store on the trace. Would you have late nights for that, or would that be?
No. For us, it's fine. It's no problem for us. If images are very big, we would have to handle it somehow. So we would have to probably downscale it to some degree, so we can still get as much useful information out of it, but not work with the original size. That might be depends. We would need to see the data, of course.
Of course, yeah.
But yeah.
More questions?
You mentioned the background subtraction in this traffic example. Is the camera, of course, is tilting to look at the place, but on the other side, the houses and the background is stable. In our case, if you think of different tapes, we will have always different backgrounds. Do you see a chance to work on this platform with any kind of background subtraction? Because I think, if I'm right, if I imagine right, 90% of all the particles are of less interest. So I think the main subject will be to optimize this kind of focusing on the interesting particles or fibers or whatever.
Yeah, but in this case we are talking about two different things. In video, when we say foreground and background, we really want to split the scene in 3D. Mm-hmm. Okay, so we want to see what are the objects moving in the foreground, let's say, and then what is the static background. But in this case, this is more about distinguishing what is of interest and what is not, because they are on the same level, right? Mm-hmm. So it's a bit different task. It will require a lot of learning, a lot of training and learning. But if we get many samples with different backgrounds, then that is possible. We need a lot of samples.
I've had some discussions with people who are doing image processing in biological stuff, in tissue and biological tissue.
Exactly.
And they were very, what's the word? They thought we had a very simple system because our background is always the same. We have a tape, transmission light, so if there's no sample, it's almost 100% transmission.
Yeah, exactly.
If there is a sample, it's less. So the background is very stable. It's not like biology, like biological tissue, where there's there's old data and you have to select two kind of systems. No, there's a background and a foreground, and the background is
it's going to be
defined.
definitely easier than in.
I think that's easier than you think.
We challenge more difficult task in the cancer study, where you have tissues, and it's very difficult to distinguish even for human which one is not affected by tumor and which one is, and because
for me, background is not, let's say, the different attenuation of the microscope settings like light attenuation of things. Background is for me the particles which are undesired. For example, think of two fibers which have a cross section. They cannot be used for an analysis according to my knowledge. So these are things which have to be reduced to focus on the particles which can be defined clearly. So I can imagine that we have to make some experiments where we give typical shapes like cells and other things to have a reference, and fibers like you have it here in your sample. But the point will be we have some which are suitable for a secondary analysis and some are not. And for me, the background is a group of, let's say, events which are not suitable for this secondary analysis. And this we have to reduce to focus on the interesting parts. So in practice, it is a kind of individual selection. I like this one and I don't like the right one. So this is, I think, the challenge of a machine analysis.
I can give you a very simple answer to that, because we have similar problem with the detection of drones. There are different flying objects. There is plane, there is bird. They are of no interest. Yeah. So what we have to do, we have to train the algorithm to recognize also those. So we have to train it also for false positives or negative samples. Yeah. So if we have something that is considered to be of non-interest, we will still have to train it as a class. And that's how it works.
I think I agree with that. Yeah, it's very easy to say, well, we are interested in that and not interested in that. But we as forensics, we are trained to be non-biased. And we still are humans, so it's not always easy to do that. But to say beforehand, now this one is not interested, we'll not look at it. I'll rather have a list. This is all in there, and I know this is fiber, I know this is glass, I know this is sand, and there's something here, class unknown. I don't know. And if there are many unknowns in a tape, then I as a microscopist could go to those unknowns and say, what is it? And maybe train the classifier further. So you might call it background, but still I would like to know that it's there, not beforehand filter it out.
Yeah, I agree with that.
Yeah, well, I'm not so. I would not be such worried about the background itself, but maybe, I mean, now you can train on cotton and acrylic and so on, but I mean, the whole variety that you have needs to be trained. So at the moment you would just recognize cotton, but you want to be interested if it's blue cotton, green cotton, yellow cotton. And also if you train a network and something appears that the network hasn't seen before, you still need to pick that up, because otherwise, I mean, if you take just tape and you have 50,000 red fibers, there's not much new information to be gained from those 50,000, but maybe one piece which you want to detect, and you need to know that. So I think the training is the challenging part.
Yeah, exactly.
If I may react to that from the consortium part, yes, you're right. You should be able to distinguish cotton and polyester and sand and glass, regardless of the color. Blue cotton, red cotton can occur in all colors. If you want to classify it regardless of the color, maybe you have to throw away the color information in the first place and then say it's cotton, and then maybe go back and measure the color to say, well, it is cotton, I've seen that, and now it's red cotton or blue cotton. So maybe there is a two-step, even if it's measured in one step, whatever. And the other bit is, yes, of course, life is very complex, and the things that we find on tapes are taken from life, so they are very complex as well. And that is exactly why we designed the two steps in the image processing bit. The graphical user interface, you have to react to load your data sets and to send your data sets, and the algorithm, the classifier bit. And for now, there will be specifications, yes, there will certainly be specifications on what you will have to recognize in the data processing, but that will not cover all of the world. That will cover a certain set of classes, and that's it for now. And we will be really happy, and it's really a step forward from our current proceedings if those are already met. But it's not everything, and we really expect that after SHUTTLE we will run and we'll build a community, and the community will have further funding or own investment, whatever, contacts with universities, contacts with companies, whatever. But if there's a community, we will have the power to develop further and say, well, algorithm version 2, or we'll have a further algorithm that can classify different kinds of crystals, because now we're interested in soil research or whatever. There will be further development, hopefully.
Yes, but to what you said, this is something we have to do anyway, because we work with different kind of low-level visual features, okay, and color is just one of them. Then it's also dominant color, but there is also things like texture, shapes, edges, and so on. So, for example, if you have a collection of cars, if you consider color, you wouldn't get any sensible results, right? So you need to consider shape of the car or different features, interest points. And then color is irrelevant. So what we do, we intelligently combine those low-level features in the training set, so it knows for car, color is not so important. So the weight factor for color is lower. But then, of course, once we, as he said, once we identify this is a car, then we can get back to color and say it's a red car. Yeah. So that will be same with fibers. So we work with different features and we process them on different levels to get some meaning, semantic meaning of it.